All right, let me ask you something that's going to sound simple, but I promise you, it's not. Why do things weigh anything at all? No, really. Think about it. Why is it harder to shove a refrigerator across your kitchen floor than it is to flick a pencil across your desk? Why does your body resist when you try to sprint? But light just flies through the universe like it owns the place, never slowing down, never getting tired. You might say, well, the fridge is heavy and the pencil is light. Sure, but that's not an answer. That's just repeating the question with fancier words. What I'm asking is deeper. What is mass? Where does it come from? Why do some things have it and others don't? For the longest time, we just shrugged and said mass is just there. Objects have it the way they have color or shape. But that answer? It falls apart the moment you look closely. Because when you zoom in, really zoom in, past the atoms, past the electrons, past everything you can see, the universe stops looking like stuff. It starts looking like energy, like motion, like fields humming with activity. And in that world, mass becomes a problem, a mystery, something that shouldn't exist at all. Now here's where it gets strange. Empty space? It's not empty. You take a box, suck out all the air, remove every last atom, strip away every photon of light, and you know what you're left with? Not nothing. You're left with something buzzing, vibrating, alive. Space itself is full. It's soaked with invisible fields, stretched across every inch of the universe like an ocean you can't see. These fields aren't things you can touch. They're more like conditions. Temperature is a field. Every point in a room has a temperature. Wind is a field. Every spot in the sky has a direction and a speed. You don't ask where the wind particle is hiding. You ask what the wind is doing right here, right now. Physics describes the universe this way. Fields everywhere. And particles? They're not little marbles. They're ripples, vibrations, disturbances in those fields, like waves on the surface of a pond. Light is one of those ripples. It has energy. It can push things, heat things, carry momentum. But here's the kicker. It has no mass. No matter how much energy you pump into a beam of light, it always moves at the same speed. You can't slow it down. You can't make it heavier. But an electron? An electron has mass. It resists being pushed. It fights back. Why? Both light and electrons are ripples in fields. Both are made of the same basic stuff: energy, motion, vibration. So why does one glide effortlessly through space while the other drags its feet like it's wading through mud? That question haunted physicists for decades. The equations that described the forces of nature, beautiful, elegant equations, they wanted particles to have no mass at all. When you try to add mass by hand, the math broke. It became inconsistent, ugly, wrong. But reality clearly disagreed. You exist. I exist. Tables, chairs, stars, they all have mass. Something had to give. To crack this, we need to talk about symmetry. Now, symmetry sounds like an art class word, but in physics, it's brutal and practical. A circle is symmetric. It looks the same no matter how you spin it. The laws of physics are symmetric. They work the same whether you're in New York or on Mars, whether it's Tuesday or Sunday. Symmetry is powerful because it limits what's possible. If you demand that something behave the same under certain changes, a lot of options just vanish. That's useful. But sometimes, reality doesn't fit the most symmetric picture. Picture this: a pencil balanced perfectly on its tip. The setup is symmetric in every direction. But the pencil never stays there. It falls. And when it falls, it picks one direction, breaking the symmetry. The laws allowed all directions equally, but the outcome didn't. This is called symmetry breaking. The laws can be symmetric even when the outcome is not. And once you see that, everything opens up. Imagine a ball sitting on top of a hill. The hill is symmetric. Every direction looks the same. But give that ball the tiniest nudge, and it rolls down into a valley. Once it's there, the symmetry is gone, even though the landscape itself was always symmetric. Fields work the same way. They have energy landscapes. And nature, like that ball, prefers the lowest energy it can find. The lowest energy state of a field is called the vacuum state. But don't let the word fool you. Vacuum doesn't mean nothing. It means calm, settled. It's the configuration where the field just sits, quietly filling all of space, like the air filling a room. Now, imagine moving through that space. Some disturbances pass right through, barely noticing the background. Others interact with it strongly. They get slowed down. They struggle. And that struggle, that looks like mass. Think of it this way. You're at a party. The room is packed with people. If you're nobody, you can walk straight across without trouble. But if you're famous, people swarm you. They slow you down. They make it harder to move. From across the room, it looks like you've gotten heavier. But nothing's been added to you. The difference is the interaction with your environment. That's what mass is. It's not coins in your pocket. It's not stored inside particles like batteries. Mass emerges from how particles interact with a field that's already there, filling every corner of space. This solves the old problem beautifully. The equations stay symmetric. The fields behave nicely. But particles still end up with mass because the vacuum itself isn't trivial. It's not zero. It's active, structured, full. Here's where calculus sneaks in, quietly, like it always does. When we talk about energy landscapes and finding the lowest state, we're really talking about finding where change stops, where slopes flatten out. Nature does this without thinking. It settles where it's most comfortable, and that settled state determines everything. So space is filled with this field. Some particles interact with it strongly and behave like they're heavy. Others barely interact at all and zip along at the speed of light, free and unburdened. Now, if this field fills all of space, it can vibrate. Just like a still lake can ripple when you toss a stone, this field can wobble around its settled value. And those wobbles, those disturbances, they show up as particles. This is a rule in modern physics. Every particle is a vibration of a field. No exceptions. The electron is a vibration. Light is a vibration. And the field we've been talking about, its vibration is a particle too. One that only appears when you slam enough energy into the system to shake the field hard enough. Most of the time, the field just sits there doing its job quietly, giving mass to electrons, to quarks, to all the particles that need it, ignoring the ones that don't. But if you hit it hard enough, you can make it ring like a bell. And that ringing, that's the particle. Now, don't make the mistake of thinking this particle is holy. Physics isn't about worship. It's about mechanism. This particle is interesting because it confirms our picture. It tells us we were right about fields, symmetry, interaction. But it's not divine. It's just real. Before we get too excited, remember something important. Every answer opens 10 new questions. Why does the field settle at this particular value and not another? Why do different particles interact with it so differently? Why this strength, this shape, this behavior? Good physics doesn't hide those questions. It puts them on display and admits, honestly, we don't know yet. But what we've learned so far, it's remarkable. Mass, something that felt so basic, so obvious, turns out to be a consequence, a byproduct of interaction. When you push a table and feel it resist, you're not just touching stuff. You're interacting with invisible fields, with symmetries, with energy landscapes all humming together beneath the surface. Now comes the next question. How do we know any of this is true? You can't scoop up space with a bucket. You can't point at the field and say, there it is. Fields are invisible. They're detected only by what they do, never by what they are. And that's not a weakness of physics. It's one of its deepest lessons. We never observe things directly. We observe effects. Think about wind. You don't see wind. You see leaves moving, flags snapping, clouds drifting. From those effects, you infer something invisible is at work. Same here. This field announces itself through consequences. And one of those consequences is a particle, a vibration. Remember what I said? Fields can vibrate. And every vibration shows up as something real, something detectable. A calm lake has a surface. Toss a stone and ripples spread out. Those ripples aren't separate objects. They're patterns in the water. But they move, they spread, they behave like things. If space is filled with this field in its settled state, then disturbances of that field must exist. They're unavoidable. Accept the field, and you accept the possibility of its vibration. And that vibration has energy behavior, rules. So the existence of the field predicts a particle, not because anyone wanted it, because logic left no other choice. If the field is real, its vibration must be real too. But this particle is unusual. Most particles, electrons, photons, exist freely. They travel far. They leave tracks. This one doesn't. It's heavy, unstable, short-lived. It appears only when you concentrate enormous energy into a tiny region of space. Why? Because making this field vibrate costs energy. A lot of it. The field sits in a steep valley. Moving it away from its calm state is like stretching a stiff spring. It resists. That resistance shows up as a heavy particle. Most of the time, the universe doesn't bother. Only under extreme conditions does the vibration briefly flash into existence, like a ripple from a boulder dropped into a calm lake. So how do you drop that boulder? You build machines. Massive machines that smash particles together at incredible speeds. Not because physicists like excess, but because there's no other way. You must concentrate energy. And energy, as you know, can reorganize into mass. When two particles collide at high energy, their motion can briefly transform into something heavier. This isn't magic, it's bookkeeping. Nature tracks energy carefully, but it lets energy change forms. A moving particle can become a heavier one for a fraction of a second, provided the energy is there. These collisions don't create the field. The field was already there. They just shake it hard enough to make its vibration visible. But detecting that vibration, that's another challenge entirely. The particle doesn't live long enough to leave a trail. It decays almost instantly into other particles, which fly off in every direction. What physicists actually see are the debris, the decay products, and from those scatter pieces, they reconstruct what must have happened. This is where statistics takes over. One collision proves nothing. Nature is noisy. Many processes produce similar outcomes. To be confident, you need millions, billions of events. You look for patterns that appear more often than chance allows. Discovery isn't a dramatic moment where someone shouts, "Eureka!" It's a slow accumulation. A small excess here, a consistent trend there, agreement across different detectors, different methods. Only when everything lines up do physicists trust the result. Probability does the heavy lifting. Averages, distributions, patterns emerging from vast numbers. Flip a coin 10 times, you learn nothing. Flip it 1,000,000 times, the truth reveals itself. And when the evidence finally becomes undeniable, the particle isn't celebrated as some isolated trophy. It's celebrated as confirmation of a picture. A picture where fields fill space, symmetries guide laws, and mass emerges from interaction, not from substance. At this point, you might think the job is done. Field exists. Particle detected. Case closed. But that's not how physics works. Every confirmed idea becomes a tool for asking better questions. Why does this field have the strength it has? If it were slightly different, atoms might not form. Chemistry might fail. Stars might never ignite. Physics doesn't answer these questions by invoking purpose or fate. It admits, plainly, we don't know yet. And that honesty? That's essential. Good physics isn't about claiming final truth. It's about narrowing ignorance in a controlled, disciplined way. Let me say something about names. When an idea gets famous, it gets labeled. Sometimes those labels are useful. Sometimes they distort. A dramatic name can suggest mystery where there's only mechanism. It can imply reverence where there's just function. In physics, no particle is sacred. Each one is a clue. Some clues are central, others peripheral. But none deserve worship. Nature doesn't arrange itself to impress us. It simply behaves. What makes this field interesting isn't that it sits at the philosophical center of existence. It's that it solves a technical problem cleanly. It lets particles have mass without wrecking the symmetries that make the theory work. That might sound modest, but in physics, modest solutions are often the most powerful. Nature prefers economy over drama. Let me also say this about understanding. Many people think that to understand physics, you must visualize everything. Little balls bouncing, waves rippling. Visualization helps, sure, but it's not required. Sometimes the right picture isn't something you can draw. Fields are like that. The metaphors, crowds in rooms, ripples on lakes, valleys and hills, they're aids to thought, not literal truth. Real understanding comes from knowing what questions make sense and what answers are allowed. It's recognizing what's essential and what's just language. One essential feature, universality. This field fills all of space. You can't turn it off in one spot and leave it on in another. Every particle everywhere is affected, whether you like it or not. Mass isn't optional. Another essential feature, selectivity. Not all particles interact the same way. Some feel the field strongly. Others barely notice it. This difference is built into the structure of things. It's not explained yet. It's observed and encoded. This selective interaction is why the universe is interesting. If everything behaved identically, there'd be no structure. Variety comes from difference. As you think about this, you might notice a pattern. Physics keeps reducing things to relationships. Not objects, but interactions. Not substances, but processes. The deeper we go, the less it makes sense to ask what something is in isolation. That shift can be uncomfortable. People like solid ground. But nature doesn't promise comfort. It offers consistency. Now, zoom out for a second. The field we've been discussing explains only part of what we observe. Most of the mass in ordinary matter comes from other effects. Energy stored in motion, in interactions between quarks. Even without this field, protons would still be heavy. The field plays a crucial role, but not an exclusive one. It's a piece of a larger puzzle. Necessary, but not the whole picture. And beyond that puzzle lie bigger questions. Gravity doesn't fit comfortably into the same framework. Neither does the dark matter that seems to dominate the universe's mass without interacting with light. These problems remain open. If you're looking for a final theory, a neat package tied with ribbon, you'll be disappointed. Physics doesn't work that way. It builds scaffolding. Some parts are sturdy. Others are temporary. All of it subject to revision. That's not failure. That's strength. It means physics is still alive. So what should you take from all this? Not the name of a particle, not the specs of a detector, but a way of thinking. When you push against something and feel resistance, remember that resistance isn't a brute fact. It's the outcome of interactions with invisible fields soaked into space itself. When you hear that something exists everywhere, don't imagine substance. Imagine condition. When you encounter mystery in physics, ask what problem it solves. And above all, stay comfortable with not knowing everything. Confusion isn't the enemy of understanding. It's the doorway. Nature is subtle, yes, but it's not malicious. Ask clear questions, listen carefully to the answers, and it'll tell you how it works. Not all at once, not without effort, but honestly, and really, that's all you can ask of the universe. If this changed how you see the world, even a little, hit that like button. Share this with someone who's curious. And subscribe, because we're just getting started peeling back the layers of reality. The universe has more secrets, and we're going hunting.